Hello, this is Patrick O'Shaughnessy, and this is the 12th module in the series Statistical Methods for Analyzing Data Obtained in the Lab or Field. In this module, we will be discussing the two-sample t-test, how to conduct it, and how to analyze it. This is one of the most commonly used statistical tests for experimental data used in the scientific realm and the literature associated with it. Here is the module map. As you can see, to get to this 12th module on two-sample t-tests, you should have already reviewed 5 previous modules, 6, 7, 9, 10, and 11. They all build towards the information associated with this module. Reviewing this all by itself would leave you with perhaps a misinformation about how to use a t-test. The single sample t-test even should be reviewed because it brings up the concept of rejection region and a p-value and those sorts of things, as well as Excel examples that will prepare you for this module here on the all-important two-sample t-test. Okay, we're going to finish up here now with two-sample t-tests. Now we're interested in whether the means of two samples differ. Not whether one sample differs from a number, but whether the mean of one sample differs from the mean of another sample. This is the classic use of a t-test. So, for example, in comparing a sample taken in one location versus a sample taken in another location. In that case, I'm going to compute a mean for the one location and a mean for another location, and I'm going to test them associated with this hypothesis technically of are there differences equal to 0 or not equal to 0, but that's equivalent to is mu1 equal to mu2 or mu1 not equal to mu2. And again, they can be tested by one-tailed or two-tailed, and again the samples must be independent and normally distributed, randomly taken, etc. Now the test statistic, again we have to boil all this down to a value that we can compare to the rejection region. Same exact scenario. Now the test statistic is a bit more sophisticated because you have to put in this difference between the two means, and you can see the standard error equation is also more sophisticated because it needs to incorporate both samples, and they may have different sample sizes, N1 and N2. And you have to pool the variance together, this equation here. Okay, all that is what it takes to now compute the test statistic. But again, the same concept. One other note is if you do this using to get at the rejection region now, same thing, go to the t-table, except the degrees of freedom is not simply n minus 1. We now have to add the two sample sizes together and subtract by 2. So it's a big number typically, much bigger than with this one sample size. Okay, so for example, is a sample of benzene from industrial plant A different from a sample from plant B? Again, we have 10 observations in each sample. We have the null and alternative established, and we state that this is going to be a two-sample t-test, and we're going to determine the rejection region now. Again, we have degrees of freedom of 10 plus 10 minus 2, which equals 18, and alpha 0.05. The tail area is 0.025 for a two-sided test, just as we saw. And so from the table, we are going to pull a number, and it's going to be 2.10092, coming off the row of 18 degrees of freedom and the column of 0.025. So now is the test statistic greater than 2.1? We'll see. Go out and conduct the experiment, gather our data, and we have determined that there is a mean of 1.82 for the first site and 2.26 for the other. Slightly different standard deviations as well. And we can now determine the test statistic by applying those extensive equations on the previous slide, and we end up with negative 2.157. Yes, that's what happens when you have to subtract, in this case, YA from YB. 1.75 is smaller, so you end up with a negative test statistic. But we put that into its absolute value form and compare to the table value, and yes, we are just able to reject the null. 2.157 is just bigger than 2.101. So you can see exactly the same approach, except we have now two samples to track. Excel does have a function for this. So you go into the data analysis tool pack and pick the tTest to sample assuming equal variance option. Put in the values for each of the two different plants and declare an alpha value. Here, go to your output range. Typically just click on this up arrow and it'll bring you back to the spreadsheet, and then you come say to here and click on it. It'll populate with this value of E3 in this case, and then you hit OK, and up pops this output. And now, like any other software for statistics, it's about how do you interpret the output. So the one interesting part about Excel output is that it gives you both one and two-sided results at the same time. Warning, only use the set you established for the test. In this case, we're interested in a two-sided situation, so ignore anything that says one tail. We're down here at two tail. And we can reject two ways, because we now have two different ways of rejecting, as we've discussed. One is to do the kind of old-fashioned approach of, is our test statistic, t-stat, the absolute value of it, greater than the t-critical, that's the value from the table, 2.101 that we just saw, and yes it is, therefore we reject. So that's one way to do it. Or you can be a little more sophisticated about it and go and look at the p-value. You see the p-value is 0.0447 or 0.045. And again, the rule there is if the p-value is smaller than your declared significance level of 0.05, you will reject. It is a smaller tail area. It must be in that rejection region, right? So reject that way. So that's how you interpret the output. Now, a note here is that there is also a t-test for unequal variances between the two samples. They may not be equivalent. So you then would use the t-test assuming unequal variances in Excel, which is another option. And again, this is actually the more common approach. It's a little more conservative. It's harder to reject. Therefore, if you do reject, no one's going to argue with you. Okay, so most people will just opt to this, although there is a test beyond the content of this course where you could check these variances actually and to see whether they're statistically different or not before you decide which one to use. But most people just opt for the unequal variances. Okay, so here's the option to use, t-test assuming unequal variances. So I just went through an example using the other one with equal variances, but now I'm telling you best to use the one with unequal variances. Same results, same way of going about it though. Lastly, we're going to talk about what's called a match pairs test. This is a special form of two-sample test. It happens because of the way the test is designed. An experiment may be designed in which the samples taken from the two populations can be paired to then compare between them. So what does this pairing mean? Well, for example, classic example, you have two instruments, same type, and you want to know, are they giving me the same results or not? So you would then perhaps give the same 10 standard solutions to this GC or whatever it is to both of them. And the comparison is then paired by the response of instrument A versus instrument B for each standard solution. as versus what we've been talking about is a random application of 10 standard solutions to instrument A, and then a completely another random set of standard solutions given to instrument B. That would be a two-sample test. This is a paired test. Another one, you have 10 workers are asked to operate machine A and machine B, and wondering which one can they produce things faster. So you could assign 10 random workers out of 100 in your factory to machine A and another 10 randomly to machine B. That would be a two-sample t-test. But if we use the same 10 workers to operate both of them, now we're pairing by worker, right? One more, traffic counts on road A are compared to counts on road B over a 7-day week. We know that the traffic differs by day. Mondays and Fridays are always a lot busier than Tuesday, Wednesday, Thursdays. So, and it's hard to randomly assign by day to the roads. So instead, they purposely pair the counts by Monday on road A, Monday road B, and then they pair by Tuesday to Tuesday, etc. So you have to know, in terms of your own experimentation, whether you are dealing with a classic two-sample t-test where you can randomly collect from two different populations, or whether you have a paired testing scenario. Now, if you do, it's very similar. You're still trying to compare between the two means, as shown here. But what you're going to end up doing, or the software will do for you, is to subtract the value of the one from the value of the other. So for the sample of day to day on a Monday road count minus the Monday road count for the other site. Right? You end up with a bunch of differences. And so you're actually back to a one sample test on these differences. So you can actually express the null this way. Are the differences equal to 0 or the difference is not equal to 0? And the test statistic looks like this, identical to a one sample test. And so lastly, for example, an industrial hygienist measures formaldehyde levels in a work area, wants to compare those levels with levels in an office area. Okay, those are the two sites, but they know that the levels may vary by day. So measurements are made across 6 different days, as shown here. And so it's work area measured on day 1 versus office area, day 1, etc. The differences then you can see are computed, their average is taken. Now, is that average different? The 0.163, is that different from 0? That was the null hypothesis. And so we go through the process, get our t statistic, and we can go to the table t, or we can go to the data analysis tool pack and ask for the t-test paired two-sample for means. And we can come down here if I'm interested in the two-tailed test and come up with a p-value, as you can see, of 0.03. That is less than 0.05. Then yes, reject. This difference is not equal to 0. Therefore, there is a difference. You see, if you reject, there is a difference between them. Okay, with that, we'll end this at the 60-minute mark and continue on with Module 5 next time.